Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 24th lecture. In this lecture, we will be continuing with static timing analysis. Specifically, in this lecture, we will be looking at slew propagation and how do we account for variations in static timing analysis. So, let us first look into slew propagation. Now, before moving to slew propagation, let us recap what is slew of a signal. So, suppose there is a signal which is rising. So, we quantify how steeply or gently a signal rises by the slew of the signal. For example, if this signal was rising very steeply, then the slew will be smaller, and if suppose the same signal was rising very gently as shown here, then the slew of the signal will be much larger. Now, in the last lecture, we had seen that given a stage, or a timing tool needs to compute its delays depending on various information or using various information. For example, if there is an inverter which is driving an interconnect and an input pin, right, this forms a stage. Now, if we want to compute the delay of this inverter, then we need to know that what is the characteristics of the incoming signal, meaning that whether it is rising fastly or steeply or gently, right. So, we need to know the slew of the incoming signal, right. Based on that and the library information and other information of the interconnect, the delay calculator will compute the output slew of the stage, right. So, now since for computing the delay for a stage, the slew is very important. The slew must be propagated in our design, meaning that given a stage, suppose this inverter was somewhere in the middle of our design. So, suppose there was a design and our inverter was lying somewhere in the middle so we know the slew of the incoming signal to our design through the constraints file, but we also need, when we want to compute the delay of this inverter, we also need to know the slew of the signal at the input of this inverter, right, and that is the motivation of carrying out slew propagation. So, static timing analysis internally needs to propagate the slew from the input ports to all the stages in the fan out in a sequential manner, and this is what is referred to as slew propagation. Now, the propagated slew can be different through different combinational paths. Okay. So, let us take a very simple example. So, a very simple example, suppose there is a NAND gate, and suppose there are 3 inputs associated with this NAND gate. Now, there are 3 arcs, timing arcs for this NAND gate, right. The first timing arc, the second and the third, right. Now, whenever the signal will come through one, let us call the input pins of the NAND gate as A, B and C. So, when the signal will come to the pin A, then that signal will encounter some delay and also have some output slew that will be exhibited at the output pin, say Z of this NAND gate, right. So, this output slew means that how fastly or how gently or how steeply the output will be rising or falling depending on what the type of signal is there at the input pin, right. So, for the arc from A to Z, there may be some output slew associated with it, meaning that the output at Z will be rising with some slew, right. Let us say that if the slew was say 10 picosecond, right. Now, for the other arc from B to Z also there will be some output slew depending on the characteristics of the timing arc B to Z and what incoming slew was there at the input pin B, right. So, let us call that the assume that the slew from output slew for the case for the timing arc B to Z is say 15 picosecond. And similarly, there will be an output slew for the arc C to Z and let us call it as say let us take a value 8 picosecond, right. So, what it means that the propagated slew can be different through different combinational path in one cell itself, right. Now, the problem is that now given that the output Z can have 3 different slews from 3 different paths, which slew to actually store for the subsequent stages. For example, there may be another NAND gate which is driven by this NAND gate. It may be again say 3 input NAND gate or it may have more than 3 inputs or even less than that, or the characteristics of this or the functionality of this driven gate may be different than what it will be, what is shown here, right. So, now to compute the delay of the subsequent stage, in this case this another NAND gate. So, let us call that this is P, Q and R, these are the pins for this NAND gate. To compute the delay of the arc P to Z, again the input slew must be known, right. Now, what should the input slew be taken for this case, because there are 3 input output slew associated with the pin Z, right, that is 10, 15 and 8 in our case, right. Now, if one solution could be that we store all 3, right, but then the problem is that if there are multiple stages, the number of slews that we need to store will go on simply multiplying. For example, for the if there are other drivers for the input pin Q, right. Here also there will be say 3 suppose this was having say 3 different input pins, then here also we will have 3 different slews, right. And similarly, there will be 3 different slews at the point R for the pin R, right. So, for the gate say let us call this gate as G2, for the gate G2 the output slew will be, if each P, Q, R has got 3 different slews, then the total slews that needs to be stored at the output of G2 will be 3 plus 3 plus 3, that is 9, right. So, it will go on simply multiplying as number of stages goes on, right. So, simply storing all the slews that are possible for the arcs within a cell, that is not possible, because the memory requirement for slew storage and propagation will simply be too high and computationally not possible, right, for practical circuits. So, in that case we have to use some other technique of storing and propagating slews in our design in static timing analysis. So, in this lecture we will be looking into that how we can do the slew propagation more efficiently. So, when we consider slew propagation, fortunately there is a property of CMOS logic gates which allows us to efficiently manipulate slews in slew propagation. And what is that property? So, the property is that the delay and output slew are typically monotonically non-decreasing function of the input slew, meaning that if there is a timing arc between say pin A to Z, then as we increase the slew at the input pin, right. Suppose the input slew was say 10 picosecond initially, then there will be some output slew and delay. For example, the output slew will be say 5 picosecond and the delay is say suppose 50 picosecond, right. Now, if we increase the input slew, if we increase the input slew say from 10 picosecond to 20 picosecond at the input pin A, then the output slew will not decrease. It is a monotonically non-decreasing function. It will be 5 picosecond or maybe somewhat higher. It will be say 8 picosecond, and similarly the delay will be non-decreasing. It will be either 50 picosecond or it will be more, right. So, it will be say suppose say 80 picosecond for a input slew of 20 picosecond, right. So, this is what we mean by saying that the timing arcs, the delay and the output slew for a timing arc is a monotonically non-decreasing function of the input slew. And what is its implication? The implication is that it allows us computing and storing and propagating only the minimum and maximum value, right. So, what it means is that suppose as in our earlier case, the slew at the from A to Z was say 10 picosecond, from B to Z it was 15 picosecond, and from C to Z it was 8 picosecond. So, rather than storing all three values, we can just store the maximum and minimum slew at the output Z, right. So, we will store only the minimum, that is 8, and the maximum, which is 50, and by just storing the minimum and maximum output slew at a output pin or at a vertex in a timing graph, we can ensure that the bound on the delay can be computed in the subsequent stages, right. So, just by using 8 and 15, if it is driving some other logic gate in its fan out, we can compute the bound on the delay of that. Why? Because delay for the circuit elements in the fan out also, those are non-decreasing function, right. So, if we compute delay corresponding to 8 and delay corresponding to 15, then the delay for any other slew that will be at the output pin Z, that will be within that range, within the range defined by 8 and 15, right. So, because of this property of CMOS logic gates, that the delay and output slews are monotonically non-decreasing function, we can obtain the bounds on the delay and output slews using the bounds on the input slew. So, on the if we store only the bounds, that is sufficient to ensure that the delay is within some bound, and as such and similarly the arrival time will be within some range, right. So, note that the purpose of static timing analysis is to ensure the safety of your circuit, and if we are able to derive the bound on the arrival time and the delays, we will be able to ensure the safety of the circuit just by the bounds, right. We do not need the exact number, and in slew propagation we utilize this property of just keeping the bounds on the slews stored at the vertices and propagating the bounds, that is it. And by propagating the bounds, we will be able to derive that what is the bound on the arrival time, and based on that we can derive that whether our circuit is meeting the setup requirement and hold requirement and so on. So, now let us look into that how the bounds are computed, right. So, let us assume that there is a timing graph and Vj is one of the vertices, let us call this is the output vertex, and then these are the incoming vertex V1 to V1, Vi to Vn. There are n incoming vertices, right. Now, for each edge we will have, for now at each vertex is in addition to the arrival time bounds, we also store the bound on the slews, right. What is the minimum slew at the vertex I, that is shown as Si min, and what is the maximum slew at the incoming vertex Vi is shown as Si max, right. So, in our last lecture we had seen that how do we derive the bound on the arrival time, right. So, the formula was a j min, the minimum bound on the arrival time at the vertex Vj is the minimum of the Ai min plus Dij min, right. So, the minimum, so each vertex will have each its own Ai min. So, we take that and add it with the minimum delay, right. So, each delay will, sorry, each edge will have associated delay, right. Now, this associated delay will be with respect to two bounds of the slews, right. One will be with respect to the lower bound on the slew and the other on the higher bound on the slew, and that is those two bounds are shown as Dij min is the lower bound on the delay obtained by lower bound on the input slew, and then Dij max corresponds to the delay obtained when the input slew was the maximum, that is Si max at Vi. So, each edge will now have, rather than one delay, two delays, one corresponding to the lower bound on the input slew, other corresponding to higher bound on the input slew. Similarly, there will be output slews bounds for each of the timing arcs, right. From the timing arc between Vi and Vj, I am showing the output slew as Os Ij min. So, this Os Ij min is corresponds to Si min, right, that the delay obtained when the input slew was Si min, right, and Os Ij max corresponds to the output slew when the incoming vertex Vi was having a slew of Si max, right. So, each edge will have now, rather than one delay number, two delays numbers corresponding to two bounds on the input slews. Similarly, the output slew will not be one number, but two numbers corresponding to two bounds on the input slew, right. Now, given that each edge has got two delay numbers and two output slew number, how do we derive the arrival time bounds? So, the arrival time bound is obtained by taking the minimum arrival time of a given vertex, add it with the minimum delay, right, and out of all the incoming vertices like V1 to Vn, take the one which is showing the minimum value, that will give us the minimum bound on the arrival time. Similarly, the maximum bound on the arrival time can be obtained by adding Ai max corresponding to a vertex with Dij max with that for that edge corresponding to this vertex, and then out of all the n input vertices, take the one which is showing the maximum, right. So, this is how the arrival time bound on the arrival time will be derived. Now, similarly, we can derive the bound on the output slew for the vertex Vj. And how do we derive it? We simply, out of all the incoming edges and incoming edges, take the one which is exhibiting the minimum slew, that is the lower bound on the slew for the vertex j, right. Similarly, out of all the n incoming vertex, we take the one which is showing the maximum slew, and that gives us the upper bound on the slew at this vertex. Okay. So, this is how we do the slew propagation from input side, that is all the Vi nodes, to the output, right. Now, let us take an example to illustrate this. Okay. So, we are, for simplicity, let us consider only the maximum bound, right, the upper bound on the slews and delays and arrival times and others. And similarly, it can be extended to the lower bound also, but for simplicity let us first take the case for the maximum case, maximum slew propagation. Okay. Let us consider that there are 3 vertices in the timing graph A, C, and these are the incoming vertices for the vertex y, and then this y is driving another vertex x, right. Now, let us assume that the maximum arrival time at the vertex A is 100, maximum arrival time at the vertex C is 20, right, and the input slew at the vertex A is 20 and the input slew at the vertex C is 40, right. Now, corresponding to this input slew of 20, the delay that is that delay corresponding to the arc A to y is 50 and the output slew is 10, right. And for the so these are the given data, assume that these exist in a circuit, then we will derive that how the slew will be propagated to the vertex y, right. Now, for the arc between C and y, the delay is 80 picosecond for the input slew of 40 picosecond and the output slew is 30 picosecond. Let us assume that this is given. Now, what will be the arrival time at the vertex y and what will be the slew, maximum slew at the vertex y? Okay, let us compute that. Now, if we consider this edge, right. So, the arrival time is 100 and delay is 50, right. So, the arrival time corresponding to this edge is 150, right, 100 plus 50, 150. For the other case from C to y, the arrival time is 20 plus delay of 80, that is 100, right. So, this is 150 and this is 100. So, if we take the max of it, we will get 150. So, the arrival time at the vertex y will be 150, right. Now, what about the slew? Now, for the edge A to y, the slew is 10 and for the edge C to y, the slew is 30. Now, out of 10 and 30, what is the maximum? The maximum is 30. So, we take the output slew as 30, right. So, this is what the slew will be propagated at the vertex y. Okay. Now, let us compute that what will be the slew and the arrival time at the vertex x. Now, to know that, we need to know the characteristics of this edge, the edge between y and x. So, let us assume that this is the characteristic, given characteristics that will be there, that is in the library, which is shown here, meaning that if the input slew at y is 10, then the delay of this arc is 30, right, delay of this timing arc is 30 and the output slew is 10. And if the input slew is 30 at y, then the delay is 100 between y to x and the output slew between y to x is 20. Let us assume that this is given in our library. Now, with this information, now we can do a slew, compute the slew at the vertex x and also the arrival time, right. So, what will be the arrival time? So, the arrival time is very easy because the arrival time at y is 150 and the output slew we know is 30. Now, corresponding to 30, we have to read this row, right. Now, in this row the delay is 100, right. So, we take the delay of this arc between y to x as 100, right. So, the arrival time at y was 150, we add 100 to it, we get a arrival time at x as 250. And what is the output slew at the vertex x? It will be simply we read this row and we get the value as 20. So, we get the arrival time at this point as 250, right, and the maximum slew as 20, right. So, this method of slew propagation based on the formula that we saw in the last slide and as illustrated, this is known as graph based analysis. So, we are computing the delays and the arrival times based on the worst case slew at a point, and based on that we are propagating it. But note here that there is a problem. The problem is that we have computed the arrival time at this vertex y through the path A to y, right. That was showing the worst arrival time 100 plus 50 we have taken as 150, not the other way path, right. But the slew that we took at the vertex y, that was coming from the edge C to y rather than A to y, right. So, the arrival time is from one edge while the maximum slew is propagating from the other edge, right. That is what is done in this calculations, right. The output slew was taken as 30 from the edge C to y, not the other, right. Now, this is somewhat pessimistic. Why it is pessimistic? Because we are the signal will either propagate through A to y or through C to y, right. That one of them will show the worst behavior, right. It is not that the arrival time behavior will be worse for one path and the slew behavior worst will be shown by the other path simultaneously. That cannot be there, right. So, the only one of these two paths will show the worst behavior, right. So, let us do a more realistic analysis by first. So, the correct way or more realistic or analysis is to consider the slew propagation and arrival time propagation first through the path A to y to x and then through the path C to y to x and then take the worst of the situation that is visible at the vertex x. That is the right way. So, now let us do the right way and see that how the computation change. So, if let us assume that the slew and the arrival time both are computed through A to y, right. So, if we compute see the path from A to y, right. So, the arrival time will be 100 plus 50, that is 150, and the slew at y will not be 30, but only 10, right. That is what is exhibited by the edge A to y. So, the slew will be here as 10 and what will be the arrival time at x and the slew at x. Now, since the slew at this point is 10, we have to read the other row in this table, right, not the lower row, but this row, right. So, if we look into this row, then the delay is 30, right. So, delay of this edge is 30. So, the arrival time at x will be 150 plus 30, that is 180, and the slew that will be obtained at x will be corresponding to this row and it will be 10, right. So, this is the correct arrival time if the signal propagates through A to y to x. Now, let us take the other case, right. Let us take the other case that is the signal is propagating through C to y and then to x. So, what will be the arrival time in this case? So, the arrival time at y will be 20 plus 80, that is 100, and the slew will be 30 corresponding to this edge, the slew will be 30. Now, since the slew is 30, we have to read this row, right, in this row in the table, right. Now, for the 30, the delay of this edge is 100, right, delay is 100 and output slew is 20. So, the arrival time at x now will be 20 plus 80, 100 plus the 100 for this edge, that will become 200, right, and the output slew at the vertex x will be 20 corresponding to this edge, right. So, we see that if we compute the arrival time and the slew exhaustively through these two paths, we will get the value as arrival time as 180 or 200, and out of them which one is worse? The worst is the 200, or the more pessimistic is the 200, right. So, the real bound on the arrival time is 200 and not 250 that we computed in the graph based analysis, right. So, graph based analysis is safe, meaning that the bound that will be given by the graph based analysis will be safe, because it is not only taking the arrival time as worst, but the slew as also the what worst could be, right, in our circuit, and therefore, the bound that we will get using the arrival using the slew propagation by graph based method will always be safe, right, but it may not be tight as illustrated in this example, because the real maximum arrival time in our circuit is 200 at the vertex x, not 250. So, what it means is that if we want to do so what typically STA tools do is that they do timing analysis based on GBA or graph based analysis. Why? Because in that case it needs to only store two values of slews at each vertex, one maximum, one minimum for one type of transition, right, and therefore, it is very efficient, and based on that it can do the timing analysis. If the design is passing the timing analysis based on GBA, then of course, our design is correct in terms of timing, there is no problem at all, right. But the bound that we get through GBA may not be a tight bound, it will have some pessimism, and to remove that pessimism, what we need to do? We need to do analysis pathwise, right. We have to analyze the path from say A to Y to X, and then C to Y to as Y to X, and then take the worst of them, right. This is just an example here, only two paths were involved, but in realistic designs there will be lots of paths, right. So, we cannot exhaustively do the timing analysis pathwise, right, by pathwise, because there are too many paths in our circuit. So, what typically design STA tools or commercial STA tools do is that they provide some mechanism to carry out path based analysis also, right. So, this is known as path based analysis or PBA. So, by default the tools do what is known as GBA, and that the timing analysis done through GBA is always safe, right, but it may contain some pessimism. As a result, we may get some artificial timing violations, and to remove those artificial timing violations, we can do what is known as path based analysis, take the path that is failing, do a timing analysis, do the timing analysis for that particular path and see that whether the constraints are whether the timing requirements are met or not. So, that will remove the pessimism of GBA, and so that will remove the pessimism of GBA, and we may be able to close the design. Okay. So, now let us look into another important feature of static timing analysis, that is to take into consideration the variations that can happen in our design. So, why do we need to take into account variations? So, because of many reasons, for example, because of say process induced variations, we are say fabricating a line which is expected to be say of thickness 1 macron, and because of the fabrication or the randomness in the fabrication process, there was some finite difference in the thickness of that line or the wire or interconnect, and as such the property of the interconnect can change. Similarly, there can be process induced variation in the devices and the transistors also, right. So, there can be process induced variations, and there can be fluctuations in temperature, the environment and the voltage in our design, right. Because of these fluctuations, so these process, voltage and temperature, these three combined together, these are known as PVT, P for process, V for voltage and T for temperature. So, PVT variations can be there in our circuit. So, because of this PVT variations, the behavior or the properties of the transistors in our circuit and also of the interconnect, those can change, right. And because of those changes, what can happen is that the timing attributes of the devices and the timing attributes of the interconnects, those can change. For example, delay, the nominal delay was say 100 picosecond, but after fabrication or because of other fluctuations in the temperature or voltage, the delay is now say 110 picosecond. So, now because of these variations in the delay, what can happen is that the constraints that were earlier passing, that can fail, right, because we did timing analysis based on our setup and hold analysis, or we checked the inequalities, whether that inequality was being satisfied or not for setup case and the hold case, and based on that we closed our design or considered our design to be timing safe. But after fabrication, there can, because of process induced variations, the delay and other parameters of the circuit can change, and the inequality which was earlier valid for our design may now become invalid. And if that happens, then it can result in failure of our circuit. So, in static timing analysis, we need to take into account this and take corrective measures, that despite some variations, our circuit is tolerant to it and does not become does not have any timing problem because of these variations. So, to tackle variations, different techniques are used in static timing analysis. So, these techniques differ in how accurate the modeling is, how much effort we need to take into account the variations in design, and what is the computational requirement for the algorithms that will run to account for these variations in static timing analysis. So, therefore, various kinds of methods are used in design flows, and we will be looking at some of these these techniques in the subsequent slides. So, the most easy way to account for variations is to add safety margins to our circuit. So, what we say is that suppose the timing requirement was that for setup requirement, the required time should be greater than the arrival time, right. So, suppose the required time was say 1000 picosecond. So, it means that the delay of the signals and arriving at the D pin of a flip flop should be such that it is less than 1000 picosecond, right. Now, by adding margin, what we mean is that we make the constraint more pessimistic. We say that okay, instead of checking for the inequality, one arrival time is less than 1000 picosecond, let us check for the inequality that arrival time is less than 900 picosecond. So, we have added an artificial pessimism of 100 picosecond, that is a safety margin, that even if the delay varies by say 100 picosecond, our circuit will still be safe, right. So, this is the very easy method of adding of ensuring the or accounting for variations in timing analysis. We add some margin. So, say in this case the margin was 100 picosecond. So, we can convey these margins to the static timing analysis tool through the constraints file, the SDC file that we write. In that we can use some constraints to specify that how much extra margin do we want in our timing analysis. So, when we add those constraints in our SDC file, then the required time will be adjusted appropriately to make it more stricter. So, in this case if the extra margin was 100 picosecond, then for setup analysis the required time will be subtracted, or 100 picosecond will be subtracted from the required time, and the new required time that will be checked by the tool will be 900 picosecond instead of say 1000 picosecond. Now, the problem with this technique is that how do we come with a good number, right? From where did we get say 100 picosecond at the first place? So, we have to do some based on past experience, we can come up with some number, but if we make it very pessimistic, because maybe say instead of say 1000 picosecond, sorry 100 picosecond as the safety margin, if we add a safety margin of say 200 picosecond, then what problems are we will what problem will be we will encounter in our design. So, the problem will be that there can be some loss in PPA. Why? Because to maintain a tighter requirement, timing requirement, we may need to change the implementation. For example, we might need to use a larger NAND gate or inverters or logic cells in our design, right, to meet the timing requirement or stricter timing requirement that is coming after adding the safety margin. So, if we add a large margin, then it is likely that there will be more area overhead, and also the power overhead can also be larger, because in this area and power are very much correlated in our design. So, we should not make the timing margin very broader or overly pessimistic. And the problem with small margin is that if we say instead of 100 picosecond, we add a margin of say 10 picosecond, right. So, that is, in that case the area penalty will not be there in our design, but the problem is that if the delay variation was more than say 10 picosecond, it was say 20 picosecond, then the arc circuit will fail, right, and therefore, there will be chances of timing failure and the yield loss. So, as a designer, we need to consider these two trade-offs while defining the margin in our circuit, right. So, typically what is done is that these margins are not very good method of adding are not very accurate method of modeling or accounting for variations in static timing analysis. So, typically we use these margins in earlier stages of the design flow. For example, during logic synthesis step, when we can use these margins, because at those stages we do not know even the delay of the interconnects, right, because we have not yet laid out the wire, and therefore, the delay of the interconnects, their capacitances are also not known. So, there are lots of uncertainty in our design, and therefore, in that case, since we do not have much information, we can use the safety margins to do the synthesis and do timing analysis in the initial stages of the design flow, and as the design flow progresses, we can reduce that margins and maybe eliminate most of those margins in the later stages of the design flow. The other method to account for variation is what is known as multi-mode multi-corner analysis, or MMMC analysis. So, what is done in multi-mode multi-corner analysis is that we carry out STA at some discrete set of scenarios. So, we do timing analysis for some discrete set of scenarios, and what are to account for variations, and what are these scenarios? So, these scenarios are derived by the combination of three things. So, what are these three things? The first one is the PVT corners for technology libraries. So, typically we use this method to account for global variations in our design, meaning that because of the process induced variation, the characteristics of all the devices in our circuit, those are shifting, right. So, that is what is known as global variations. All are making, for example, all the devices in our circuit are fabricated such that they take the worst delay or the maximum delay or the best delay or the typical delay, right. So, if the variations are of global types, then what we do is that we have libraries not only of one, we do not have only one library, but we have a set of libraries for various corners. Maybe we can have a library for the worst case, meaning that the .lib file for the worst case will have the timing attributes of all the cells in the library for the worst case, meaning that the delay will be larger or will be the highest or the worst for the various timing arcs in our design for setup analysis, right. Similarly, there can be a best library for the best case, or there can be a library for the typical case, right. So, there will be a set of libraries for different corners, and we use those set of libraries to derive the scenarios. How we will derive the scenario, we will just see, and then do the timing analysis. So, the first thing is the set of libraries for various PVT corners, and the second thing is the multiple modes of our design. So, our design may be working in various kinds of modes. For example, it can work in a functional mode, meaning that it is doing the function, carrying out the normal functionality of our design, or it is working in a test mode when it is doing for, say, going for DFT, or it is in the sleep mode. For example, if we want that our chip is not doing some active computation, to save power we can take it to a sleep mode, or we want to do a very high performance job, the requirement is that the chip deliver the maximum performance, then there can be, say, a turbo mode, or there can be various modes in our circuit. So, in these different modes, what is the basic differences? So, differences will be respect to, say, the clock frequency. The clock frequency in the, say, turbo mode will be the maximum, and in the sleep mode it will be minimum, or some controlling signal will be taking some value. For example, in the sleep mode there will be some signal called sleep which will be high, right, which will make most of our circuit as switched off, or so on. So, there will be some controlling signal which will take a constant value, or and the clock frequencies and other things can change in our design for different modes, and those kind of effects are taken into account by writing different SDC files. So, there will be an SDC file or the constraint file for the functional mode, another SDC file for the test mode, another for sleep mode, another for turbo mode. Right. So, these different SDC files define various modes in our design. And then the third one is the RC corners. So, RC corners, so in the last lecture we saw that the parasitics needs or the interconnect parasitics are important for computing the delay of a stage, and those parasitics are extracted using a tool which is known as parasitic extraction tool. Now, the characteristics of this parasitics, for example, a metal wire is very much dependent on the how it is fabricated. For example, there will be small deviations in the thickness, in the width of these lines, and because of those the RC values or the capacitance and resistance values of the interconnects can change. So, to account for that, what we do is that we do not extract one parasitic file for our design. We extract multiple parasitic files for different what is known as RC corner. R stands for resistance, C for capacitance. So, for various RC corners we extract different SPEF file or a standard parasitic exchange format files which contains the parasitic information of the interconnect. For example, there can be a parasitic in a SPEF file for the minimum capacitance case, for another can be for the maximum capacitance case, and so on, right. So, using these three things, or the PVT corners, multiple modes and RC corners, we derive scenarios. How do we derive it? Let us take an example. Suppose in our design there were three corners and three .lib file. One was, say, slow.lib, the other was fast.lib, and third one was, say, typical.lib. And there were, say, 4 modes in our design. So, we will have func.sdc for functional mode, then we have, say, test.sdc for the test mode, and then we have, say, sleep.sdc for the sleep mode, and a turbo.sdc for the turbo mode. Similarly, suppose there are four parasitic extraction corner, maybe one is C worst, capacitance worst dot spef, then C best dot spef, and then, say, RC max dot spef and RC min dot spef. Now, these are discrete set of variations that we want to analyze in our design. So, using these three corners, 4 modes and 4 RC corners, we can derive 3 into 4 into 4, that is 48 scenarios by combining, for example, slow.lib, then func.sdc and C verse dot spef and so on. So, we take each combination of this, and then we can derive say 48 scenarios out of it, right. So, one of the ways is to analyze or do perform STF 48 times, right, for each of the scenarios, but that will be inefficient. So, rather than doing 48 different STA or timing analysis, what we do is that we carry out static timing analysis using what is known as multi-mode, multi-corner analysis simultaneously for all the 48 scenarios. And as a result, what it will become more efficient. Why? Because we need for the 48 scenarios that we got, we need not analyze all of them. If one of them is dominating others, see, the purpose of static timing analysis is to ensure the safety, right. If the safety of one scenario can tell us that what conditions for other scenarios need not be evaluated, then we are still safe by just analyzing one of the scenarios out of them, right. So, what MMMC analysis does is that it avoids computation of dominated scenarios. If one scenario is dominated by some others, then that dominated scenario need not be evaluated separately, and therefore, computation can be saved. Also, the parallel processing can be invoked, and all these corners can be all these scenarios can be evaluated in parallel using multi-processing or parallel processing, and we can efficiently derive the safety of our design for all 48 scenarios rather by doing MMMC analysis rather than explicitly analyzing separately for all 48 scenarios. Okay. So, commercial tools typically give us flexibility to do such kind of multi-mode, multi-corner analysis in the design flow, and this method is one of the most popular method of accounting for variations in our design. Now, the method that we saw for MMMC analysis, that is effective if there are global variations, meaning that all the devices are being affected in one particular manner, all are showing the say worst delay or best delay or so, right. So, that is kind of global variations, but we also need to account for local variations in the properties of devices and interconnects. Why? Because when we fabricate devices, say transistors, and our chip is containing say millions of transistors and lots of interconnects, then there will be some local variations in their properties because of random effects, random fluctuations, right. And we cannot avoid that, we have to tackle that in our design. So, to tackle these local variations, what we do is that we define on chip variations derate, right. So, we say that there is some derate factors associated with the delays, and we are making our analysis somewhat pessimistic by applying this derating factor. So, when we supply derate value to the timing analysis tool, then what it does internally is that it computes effective delay. And how does it compute an effective delay? It is the effective delay is computed by multiplying the nominal delay with the OCV derating factor that we have given for our design, right. Now, this OCV derating factor can be based on say path bounds, meaning that we can say that for early some derating factor is used, and for late paths some other derating factor is used, right. Similarly, we can say that for data path use some derating factor, for clock path use some other derating factor, right. So, we can make these derating factors selective based on the path type or path bounds, and also delay type. Maybe we want to derate the gate delay by say 10%, while interconnect delay we want to derate by say 5%. So, those kind of things typically STA commercial STA tools provide us those facility that how we can define derate for different situations or different types of path or different types of timing arcs. And different, we can also define or different OCV derating factors for say best case or worst case or typical case. We can specify different numbers for them. So, let us take an example that how do we specify derating factors and what will its impact on timing. So, let us say that in our when we are running a tool, we have specified that for the late path the derating factor is 1.1 and for the early path the derating factor is 0.9. So, what it means is that for the late path, suppose the delay was 100, it will multiply by 1.1 and the delay will be taken as 110, right. So, this is the derating factor, and for the early path, suppose the delay was 100, then the derating factor is 0.9, then it will take a the delay as effective delay as 90, right. Now, this kind of specification will impact the setup analysis and hold analysis in different ways. So, in setup analysis, what are the late paths? So, the late paths are the paths which are for that we use for the data path and the clock launch path, right. So, those are the late path. That is what, if we want to if we consider the constraint for setup analysis, then if the data path and the clock launch path those become late, then the design is more likely to fail, right. And therefore, this data path and clock launch path are taken as late path, and the derating factor of 1.1 will be applied, meaning that if there was an AND gate on the data path and its nominal delay was 100, then that AND gate's delay will now be taken as 110 rather than 100, right. So, it will be multiplied by the derating factor of 1.1. However, on the clock path, capture path, the delay will be derated by 0.9. For example, if we have say flip flop, this is the launch flip flop, and through combinational logic it is being captured by a capture flip flop, and there is a say inverter or a chain of inverter on the capture clock path. So, if we want to do a setup analysis, then if we decrease the delay of the circuit elements on the capture clock path, then the analysis the circuit will be more likely to fail, right. So, suppose the delay of this inverter was 100 picosecond, right. So, because the early part derating is 0.9, the delay of this inverter will now be taken as 90, it will be multiplied by 0.9, right, and it will be taken as 90 as the effective delay, right. Similarly, for the other inverter, it will be derated by a factor of 0.9, right. Now, in the hold analysis, similarly for the for the data path and the clock launch path, and those become the early path, right, and if it is derated by 0.9, then it is more likely to fail, right. And similarly, for the clock capture path, that is multiplied by 1.1, because then the circuit will be more likely to fail, right. So, for hold analysis, for the data path becomes the early path, right, and therefore, for the derating factor of 0.9 is used, right. So, if we want to look more or on these things, you can refer to these references that I have shown here. Now, to summarize in this lecture what we have done. So, what we have looked into two important aspects of static timing analysis. The first is that how slew propagation is done, and we looked into two modes of slew propagation. The GBA method, which is computationally more efficient and widely used, but may not give a tighter bound or may contain some pessimism, and the other is the path based analysis based slew propagation, which is in which the slew is propagated depending on the path we are analyzing. So, the arrival time and the slew will be propagated through the same path, right, and it is more accurate, right. And then we also looked into some of the techniques to account for variations in our in static timing analysis. So, in the next lecture we will be looking into the constraints. So, we have in the earlier lectures we have discussed that constraints is the basic information from which static timing analysis infers the timing constraints that we want our circuit to follow or obey. So, in the next lecture we will see that how we can write those constraints and convey that information to the static timing analysis. Thank you very much.